the previous notebook, we showed how to work with the output of volatility in plugins like PSList, Suspicious Threads, and Malfind. And we showed how to process and transform this data using DuckDB and IBIS inside of Maremo. While there are a lot of different volatility plugins, there is still a lot of data in the memory dump, which is more unstructured. So one category of such data is textual data, strings. So just think of everything that at some point in time must be represented as a string in memory. So that could be the contents of a notebook. It could be a URL, a file name, a file path, an email address. At some point in time, it has to be a string and it has to be in memory. And in fact, even if a process terminates, then it's not like that memory region will be automatically zeroed out. That will happen when that region is allocated by another process. So that means that you can actually find string data and other data from terminated processes. So the way we work with this type of data is that we can extract the ASCII and Unicode strings directly from the memory dump. But working with a large collection of strings can quickly become unmanageable. So in order to address this, in this notebook, we will be creating tools for textual data to help us make this process more easy for the analyst. Okay, so let's tie this back into our ongoing investigation. So in the previous notebook, we ran this suspicious thread output plugin, and the output is shown here. As we explained, what this suggests is that there's some sort of process injection going on for the Explorer and OneDrive processes. And that is associated with these VADs here. So these are memory regions. And then what we can do next, have the suspicious threads, we know the associated VADs. Now we can run another plugin called VADinfo. And if you run that plugin with the PID and dump flags, you limit the output to just certain PIDs. In this case, it's Explorer and OneDrive. And you dump the contents of each VAD to a file. So in this case, we just ran it for both Explorer and XE, and we dumped all the VADs for those two processes. So we can see, like, this VAD starting at this address and ending at this address for Explorer is written to this file. And now we need to extract the strings. So we will just reuse some functions from Floss, which is actually a very sophisticated string extraction library, but it's meant for extracting string contents from binary files or shellcode whose string contents is obfuscated. It has functionality for trying to recover these. However, in our case, all that functionality is not super relevant because we are working with memory dump. So our assumption is that, even if the malware packed something or obfuscated something in its binary, at some point it needs to deobfuscate this to make it useful, to use the actual string contents. So the assumption is that when we initiated the dump, this was already done. So we can proceed by just scanning for any ASCII and Unicode strings. Initially, we will just do this for the VADs that were flagged as suspicious. So we do a join. We join together the suspicious thread output with the VADs, and as a join condition. So these two are the files that we will extract strings from. Let's just create a utility function for doing this. Again, you can see we are just importing some two functions from the Floss library for extracting ASCII and Unicode strings. These are actually super simple functions that just do some regular expression operations. So we can see that we just read the contents and then either call the ASCII extraction method or the Unicode extraction method, depending on this argument. And then we return the whole contents of that particular file as one large string. So just to demonstrate how this works, let's do like this function to just do this for, let's say, the first file. Let's see how it looks. Typo here, like this. So you can see that what we get back is all the ASCII contents concatenated as a single string, and then you can vary the min length argument like this to get just strings longer than X characters, and you can say Unicode here to just get the Unicode contents instead. So now we need another feature. So we have defined this utility function for extracting these strings from VAD files, and now we actually want to work with tables. So we want to create a string table that has this schema. It has the ID, just the ID of the row, then it has the file name of the VAD that contains these strings. Then we have an ASCII column containing all the ASCII strings of that file concatenated together, and then we have a Unicode column that similarly has all the Unicode strings concatenated together. So what happens here is that we've defined a create strings table function which takes a list of files, and then it just iterates through them and calling the extract strings from VAD utility function that we defined using both the ASCII and Unicode mode. And then from this resulting list of rows, basically, we create a DuckDB table, and you can see how it looks here. So in this case, we just gave it two VADs, so this one, and then we ran the extraction, and you can see that the result is this table structure here, where we have one row for each file name, and then we have an ASCII column with all these ASCII strings concatenated together, and we have a Unicode column with all the Unicode strings concatenated together. I want to take a moment here to revisit the row viewer, because we talked about that in I think the first or second notebook, like how this could be useful if you have certain columns which are large, they have a lot of content. So here you can see like this was really big, but this is all the ASCII data for this file name. You can see here it has a lot of things, like it looks like junk, and it has some something that looks like it comes from some C++ function names and C++ standard library stuff, and then you have something that looks kind of weird, like these strings here. You have some file names, process names, and then similarly you have a Unicode's column. So I just want to show you the row viewer again, how it could be useful for displaying more columns which have large values, basically a lot of textual values. It's fairly easy to go from what we have to one row per string. So the way you do this is to split the for example, if you want to create this type of representation for all the ASCII contents, you would use the split column for on the ASCII column to create an array containing one string per element, basically. And then you would unnest the array, so that would create one row per element in the array. So to easier demonstrate this, let's say we start from this table, strings from suspicious VADs. We redefine the ASCII column by using, the existing ASCII field, this concatenated, all the concatenated ASCII strings. We use split operation and using the whitespace delimiter. So the result of this is just a column whose content is a array of strings, And then by calling the unnest operation here, it turns this column into basically for each entry in that list, it will create a row. So it changes the entire table. And then we have a filter here, which just, any string which is shorter than 5 in length, discard it. And then we do a distinction operation on ASCII, and we just drop the Unicode symbol. Otherwise, we will have a Unicode row containing all the Unicode stuff for each row here. So now even like this table is kind of useful to work with, because you can do simple searches. Like I think we have like thumbs something. Yeah, you can see we have this file names that we looked at before, and we had these weird looking strings like this. It's kind of rudimentary when it comes to doing string operations. The alternative being working on the Unix command line, which is very powerful if you're kind of like a Unix wizard. But yeah, just if you go back to what you learned in the previous notebook about combining the Marimo UI elements, the reactive execution models with DuckDB, you can already think here, what sort of UI elements can you create for making the investigation of the string contents more manageable. The way we think about this here is just that we just want to look for certain artifacts. We want to create functionality that lets us search for example, email addresses, URLs, and so forth. So in order to make this happen, we have, we're just using DuckDB regular expressions and then we defined a function that tries to extract any URLs, any email addresses. We have another one for extracting IP4 version addresses, file paths, file extension, DLLs, and so on. And then we simply take this list of what we call extractors, and we just evaluate them on both the ASCII and Unicode tables for each of the pattern extractors. So for the email, for the URL, and for the IPv version 4, it creates a new column in the data stream. There you go. And then you can see the result here as a data frame. You see, okay, we have the file name, then you have one column for the URL extractors, the email extractor, the IPv version 4 extractor, and here you can see for Windows paths, it has some entries. So the contents of these columns is a list of all the matches in the ASCII strings for that regular expression pattern. And similarly, you have some files. So you can see here, thumbs file we talked about. You have the pattern that looked for exe files and DLLs. It's found like command.exe slingshot DLL, which looks a bit weird. And then you have the other stuff. Okay, good. So we have this table now that contains one column for each of the extractors, but we want the user experience to be more, pleasant for the analyst. So let's introduce some Marimo widgets. So for example, we want to give the user the option to say, okay, I want to look at the results for just the email extractors. So I just want to look at the emails that we have extracted. And I also want an option to select the minimum length. So for example, if you're looking for URLs, I want to be like, yeah, the URLs should be greater than 10 in size, basically. Everything else is filtered out. So in order to achieve this, we need to introduce a drop-down menu, which we've looked at before, where the options are, each of these values here. And then we have, as before as well, the length selector is just a slider component like this. Okay, so next what we want to do is to actually tie everything together. So we create again a utility function. I guess we call it create table here, which takes the extracted string, so this representation in, and then we take this component, the drop-down menu in, and we take the length slider in. and then we just extract the whatever category the user has selected. Could be URLs, could be Windows paths. So we just extract that column, and then we do the unlist operation as we explained before. So for each of those entries in this list, we create a new row, and then from that new table expression, we basically want to filter out any entry that is less than whatever width we have specified using the slider component. So this is this, and then we want to render this as a table representation. Okay, we are introducing some custom HTML just to give it a flexbox layout, where we have on here left hand side we have the drop down menu where you can choose which category or pattern extractor to display the results for example the Windows path like this, and then we have the slider here on the and everything here is contained within 600 pixels, so it doesn't grow to the entire width of the cell. The slide is up. You can see, hey, okay, there's only these entries that are greater or equal to 12 in length, and so I can see that the longest one is called slingshot dll.dll. Okay, so this was just the results from the two suspicious VADs. So those VADs that were associated to the output from the suspicious thread plugin. Let's run it now on all the VADs from these two processes. So let's filter out anything that isn't explorer.exe or wonder.exe and get those files. So the contents of the file output again. Now, extracting strings can be slow if you're doing like thousands of these different dumps. So we need to guard ourselves against a situation where we have a slider, and every time we change the slider, we basically re-execute the extractions. So Marimo has this built-in functionality, which is this stop function. So if this condition is false, the rest of the execution won't execute. And then it has a run button. So the run button is such that if you click this, the value attribute will be set to true. Then it will immediately be reset. So what happens then is that if you click this, it sets the value attribute pass. This condition will pass, so the rest of the cell will be executed. So if I do this now, you can see it doesn't take that long for this particular memory dump, but imagine we had the VADs for all the processes, for instance. Okay, so when I click this, it reran. If I just try and rerun it automatically, nothing happens. So then you get this. This cell wasn't run because an ancestor was stopped. So click this again. I've been like 11 seconds, about 11 seconds, I think it was. So this is the results from all the VADs for those two processes. So here I think we get some URLs, for example. And then you can go like, again, to use this. You can do filter by values. Let me just look at the stuff from these two. That's not very interesting. Actually, let me go for this one instead. There's nothing. Oh yeah, let's reset this. Let's look at any archive data. No, nothing. URLs, nothing, because I'm just looking at this memory dump. But yeah, that should get the point across, I think. So with the takeaway here was, with relatively little custom code, we can create these ad hoc, very powerful interfaces that assists in the forensics work. Now it's your turn. So go through the examples we showed above, and now extend this by building a small viewer that browses both Unicode and ASCII strings side by side. So what you want is this interface here, is basically. Now, always keep in mind that we're not limited to the functionality of DuckDB, especially since we're just working with very small data sets. So sometimes it's simpler to just use plain Python structures, lists, sets, dictionaries, and so on, and also to work with existing Python packages that we just download. So as an example, let's focus on the URLs. So here are two Python packages for working with URLs. So you have TLD extract, which is for parsing URLs, and then you have the Tranco package, which provides basically a ranking of domains. So you can retrieve, let's say, the top 1 million popular domains, similar to the Alexa datasets. So for example, here we are importing TLD extract, then we are importing the Tranco package, and then we are downloading the current, Tranco datasets basically. So here you can see like what Tranco provides. It's the top 10 domains. So the most popular domain, apparently google.com. Surprisingly, microsoft.com is a very popular domain. I'm not sure like what data this is based on, but it does give you some external data to use for enrichment in your investigations. So that's the point. Okay, great. So at this point, we have the all extracted strings data frame, which is the output of running all the pattern extractors. So we have the URLs, which is a string of all the URLs extracted. The emails column is all the emails extracted. And now we want to just get all the unique URLs in a Python list. So let's get rid of this. So what we do is we do a filter operation to drop every row whose URL column has length 0. So it's an empty array. And then we select the URLs and run the unnest operation. So for each entry in this URL array, we create a new record basically. And then we run the distinct operation to just retain unique strings. And then we can convert this result to a Python list. So the result, just to look at this, would be, if we look at the 5 first entries, it would be something like this. So now we want to just show how we would combine TLD extract and a Tranco. So let's create a utility function. So what it does, it takes a URL, so just a string as input, and then it does the parsing using TLD extract. So you pass it the URL and you get back some TLD extracted object. So you can see here that what we actually have is the ability to get access to the subdomain, the domain, the suffix, the registered domain, and so on. So and then we can also add information about, is the registered domain actually in the list of top 100 domains. So if we test this function using entry 10 of our URL list, we see, okay, what we pass in is this, and then we use TLD extract to get these entries, and then we check this one against the list of top 100 domains. So here we've done, something very simple by piggybacking on these existing packages. So that's the sort of takeaway here. So we can apply this to all the URLs in the dump. So you can see here, we just run this for all the URLs, and then we actually just pass this to a mem table, which is in-memory IBIS table. This one is actually backed by pandas, but it doesn't really matter because we just need to pass it to the table function to visualize it. So we can see here, we're going to Python, and now we're going back to data frames. I think you can actually, let's see if we can actually just do this probably instead. So we can just pass it. Yeah, we can just pass also just a regular list to the table function basically. So there was no need to use memtable here, but yeah. Now we're back in sort of familiar territory where we can we have this enriched list of URLs to look through. Okay, so let's get back to analyzing the memory dump we have. So use the table above to look for domains that are suspicious. If you need to, then create additional transformation and enrichment functions. And once you've found the domain, then we encourage you to check if this domain is present in any other process, WAD files, or anywhere else in the memory dump. So let's continue writing more custom tools. So for the idea here for the highlighting section is simply to create a search bar that lets us type in a word or pattern, and then any such occurrence will be highlighted in the actual text contents. So to do this, we need some mechanism of highlighting text. This is available via the mark HTML element. So let's create a function highlight text, which takes a text string as inputs and then the search term. And then the idea here is just to, if you pass in a non-empty search term, we will create a regular expression pattern. And then, we would just substitute every occurrence of the search term with this HTML basically. So we just insert a mark element with what we, with the match basically. So it's sort of a replacement operation. And then the entire function just returns some HTML. So if there's occurrence that we have found, then we will insert this. Otherwise, we will just return like a div with the actual text itself. Okay, next we need a input field. So we can use the Marimo text widget like this. There's an existing UI component, and then we need to pass in a debounce argument, which basically tells Marimo to wait X amount of milliseconds after the user has stopped typing before updating the value. Otherwise, it would, as you type, keep trying to rerun every cell that depends on the search term input value attribute basically. Okay, so let's do like a test case. We extract the first Unicode string from the data frame, which is fine. So you can see here. Let's see, this here is just calling the utility function that we created. And then we are just stacking the input field and the highlighted text component that we created on top of each other. So in practice, what we get is this. Let's see, we write something like coordinated like this, and you can see that what happens is that this function runs and it uses the search term input value as input, and it applies the regular expression here and replaces every occurrence with this mark HTML element, and this is the effect we get. So again, this is not a lot of code. It's some very basic HTML out of the box elements with some coloring and CSS attributes, which makes something could be very useful. There you go. So at this point, you have enough components to build another data app. So what we want you to build here is a type of custom search engine for the VADs. So the user interface that we suggest is the following. So present the user with a list of VADs, let them select one VAD at a time by clicking them. And then there's a search bar that lets you provide a regular expression that is evaluated on the contents of the strings contained in that VAD. And then you highlight those in another component for the user. So for inspiration, you can look at the previous notebook that went through the initial triage overview dashboard, and feel free to expand this. Go as far as you want. This is, I think you can make something really cool out of this. And with that, we've come to the end of the notebook about strings. This is Working with string data, investigating string data is a very important part of memory dumps. It's a non-optional step, basically. This is a sort of a wealth of information, and there's a ton of things you can automate and really build to make the whole process more manageable. If you want to take this further, perhaps you can do something like dumping the file cache and create some sort of search engine on top of this, either by just using Python here in the notebook or by tapping into some full text search engines. Feel free to share anything that you build on the Discord or on social media.